Welcome back. Dear students, I was just explaining you what is DL isomerism, where we take the position of the hydroxyl group around the asymmetric carbon atom and we do not consider the optical rotation. So, that is not same as optical isomerism, but we call it DL isomerism. Here the reference molecule is D-glyceraldehyde. Here you mark it is capital D, and it is, we are not saying the small d. Small d indicates optical rotation, small l indicates optical rotation, but capital D indicates position of the hydroxyl group and position of the hydroxyl group in the farthest asymmetric carbon atom. So, also L indicates, capital L indicates the position of the hydroxyl group in the around the farthest asymmetric carbon atom. So, any molecule we consider, we have to check whether it is conforming or it is at par with the D-glyceraldehyde or L-glyceraldehyde. If it is similar to D-glyceraldehyde, then we consider this to be the D isomer. If it is similar to L-glyceraldehyde, then it is similar to, or we can call it L isomer. Say for instance, I take an amino acid. I am just going to amino acid. I take one amino acid. So, this amino acid so if we take this one is asymmetric. This carbon atom is asymmetric carbon atom. Well, this is the alpha carbon. This carbon is called alpha carbon. This alpha carbon is asymmetric, and this alpha carbon, if we check the position of the NH2 amino group and the hydrogen, then we can say that it is similar to this one or this one. You just check whether it is similar to this one or whether this is similar to this one. We will find as it is HCNH2, so HCOH or OHCH, it is definitely similar to this one. If it is, then we will call it D amino acid. But if it is otherwise, say this is, if it is like this, then this one is similar to this one. It is similar to this one. Then we call it L amino acid. In all the proteins we have, all the amino acids in our proteins are of this category, L amino acid. So, like this, many biomolecules will have either D form or the L form. Wherever necessary, we have to ascertain that. Coming back to monosaccharides, once again, monosaccharides, we will now see what are varieties of or what are the isomers present there. Now, certain things we will check first. First thing is the isomers. First thing is the isomers. In case of trioges, in case of tetroges, then in case of pentoges and hexoges, very common. I am just touching the common ones. Trioges, just I have described. Aldotriose is this one. we will have the D-glyceraldehyde and L-glyceraldehyde. Aldotriose will have the D-glyceraldehyde and L-glyceraldehyde. So now whenever I say D, take it that I am speaking about the capital D, and when I am speaking L-glyceraldehyde, always take it that I am speaking about capital L, means configuration around the farthest asymmetric carbon atom. That is what I am speaking of, not the optical rotation. Now when we come to ketotriose, I have already shown you they do not have, there is no asymmetric carbon atom, so no isomer. But when we come to tetrose, pentose, hexoses, in case of tetroses, what will happen? Now there will be aldotetrose. In case of aldo, there will be how many asymmetric carbon atom? Number of asymmetric carbon atom is equal to, this is the number of carbon atom minus 2. So here number of carbon atom is 4, so minus 2 is equal to 2. So number of asymmetric carbon atom how many? It is equal to 2. When we come to keto, number of asymmetric carbon atom is how much? How many will be there? It will be same thing, number of carbon atom minus 3. So 4 minus 3 is equal to 1. So number of asymmetric carbon atom will be number 1. So when we come to pentose, it is, if it is aldose, so 5 minus 2 is equal to 3. If it is ketopentose, then it will be 5 minus 3 is equal to 2. When we come similarly to aldohexose, it will be 6 minus 2 is equal to 4, and here when it is ketohexose, here it will be 6 minus 3 is equal to 3. So these are the number of asymmetric carbon atom in each category. Well, in case of tetrose, it will be 2 or 1. In case of triose, it is already 1. And ketotriose, there is nil because 3 minus 3. 3 minus 3 is equal to 0. It is 3 minus 2 is equal to 1. Here 4 minus 2 is equal to 2. 4 minus 3 is equal to 1. So in this manner, we will have the asymmetric carbon atom. Now once we have learned number of asymmetric carbon atom, the next task is how many isomers are going to be formed. How many isomers are going to be formed. So how to find it out? We can find out in a very simple manner. That is what we will have. We will have the 2 to the power number of asymmetric carbon atom. 2 to the power number of asymmetric carbon atom. So now continue with this pentose. Well, let us say now have the triose. Triose, we will write here aldo, then here we will write keto. Well, let us make a table like this. So if it is triose, then in case of aldotriose, there will be number of asymmetric carbon atom and number of isomer. asymmetric carbon atom and number of isomer. Let us check. So, in case of triose, number of asymmetric carbon atom is 3 minus 2 is equal to 1. Isomer will be 2 to the power 1 is equal to 2. Here asymmetric carbon atom is 3 minus 3 is equal to 0, so isomer will be nil. Now when we go for tetrose, here what will happen? It is 4 minus 2 is equal to 2, 2 to the power 2, 2 to the power 2 is equal to 4. So 4 isomers will be possible here. Now when we coming to the keto, here it will be 4 minus 3 is equal to 1. So here it will be 2 to the power 1 is equal to 2. Now we come to pentose. 5 minus 2 is equal to 3. 2 to the power 3 is equal to 8. Now here it will be 5 minus 3 is equal to 2. 2 to the power 2 is equal to 4. So now coming to hexose. 6 minus 2 is equal to 4. So 2 to the power 4 is equal to 16. 6 minus 3 is equal to 3. So 2 to the power 3 is equal to 8. So this is what table is like this. You simply check it. I hope you are following it properly. We can have it like this. So if we have a triose, then there will be 3 carbon atoms out of minus 2. So 1 asymmetric carbon atom. So now 2 to the power number of asymmetric carbon atom. So this is 2. So this is, we have already seen they are what? They are one D-glyceraldehyde and another one is L-glyceraldehyde. And here it is 0. 3 minus 3 is equal to 0. So there will be no isomer. Now when coming to the tetrose, this will be 2 asymmetric carbon atom. So 4 isomers. Now what are these 4 isomers? We will draw the structure of these 4 isomers and we will remember their names too. Now what happens? Out of these 4, 2 will be D and 2 will be L. 2 will be D and 2 will be L. Out of these 8 similarly, 4 will be D and 4 will be L. And here 8 will be D and 8 will be L. Now how to, if we know the structure of D, we can know the structure of L. How? Take a mirror image. How to do it? Take simply a mirror image, because here D-glyceraldehyde and L-glyceraldehyde, they are mirror image. Mirror image, you know, our left hand looks like right hand. So if it is on the right side, it will be on the left side. It is on our right side, so it will be on the left side. So as they are the mirror image, so in every case, whenever there is a D isomer, there is also an L isomer. We simply take its mirror image. So here will be 4 D isomer and 4 L isomer. And out of this 16, 8 D isomer and 8 L isomer. Similarly here, this is 2 out of these 2. So 1 is D, 1 is L. Here again 2 are D and 2 are L. Here again 4 are D and 4 are L. What happens in nature? If we examine nature, these monosaccharides, we will find an interesting phenomenon. What is that? Almost all monosaccharides are available in D form. Almost all are available in D form. That is why what we do, we learn the structure of D form. And for any other purposes, whenever we require the L isomer of a D isomer, what we do is we simply take a mirror image and get it. For example, I will go first the tetrose. Triose I have already discussed. I will now go for the tetrose. So now, we are just discussing the tetrose. So number of carbon atom is 4, number of asymmetric carbon atom is 2. So what will happen? There will be 2 to the power 2, that is 4 isomers, and out of these 4, 2 will be D isomer and 2 will be L isomer. So we will first see these 2 D isomers, and once we know the D isomers, automatically we can get the L isomer by simply taking a mirror image of that. I will just show you how we do it. Now these 2 D isomers, we must have the name specific for them. I'm just coming to that. First let us draw it. So CHO, remember one thing, when we are saying that they are a D isomer, so the configuration around this farthest asymmetric carbon atom is fixed, this one. We are not going to alter this one, alright. We are not going to alter this configuration around this farthest asymmetric carbon atom. So now another one will be, we simply change here in the carbon atom number 2. This is your carbon atom number 1, this is 2, this is 3 and this is 4. So this third one is fixed for D here in this particular case. Just examine these 2 molecules. Examine these 2 molecules. They are same at the farthest asymmetric carbon atom. This implies they are D isomer. So I can write here D. Because of this configuration HCOH. So for this we can write here at the D. Now for this one and this one, you just examine, they are reversed. These 2 are reversed. So this one we call erythrose. And this one again D, this is D, threose. We are supposed to have 2 D isomers. So these are 2 D isomers. And we are also supposed to have 2 L isomers. And these 2 L isomers will be what? L erythrose. I am writing it here. One is L erythrose and L threose. Which one is L erythrose and which one is L threose? How to get it? How to get their structure? It is very simple. You take the D erythrose, put a mirror, say I put a mirror here, then I get a structure. What I will get? CHO is fixed. Now this one will change, this one will change. So what it will be? It will be H this side, OH this side, and this will also change. H this side, OH this side, and CH2OH fix. So this is your L erythrose. Now how to get this L threose? This L threose will be, I put again a mirror here and I get the structure CHO and C and H this side. Just you see mirror image of this one, and OH this side. Here it will be the H, and here it will be the OH, CH2OH. This is your L3Os. So they are their pairs. So this is your L-erythros and this is your L3Os. Well, now this is the manner in which we can get or we can write down the structure of L configuration, structure of L isomer of every D isomer. I need not tell it once again. Then we go for pentoses. I'll go for pentoses. When we come to pentose, one more thing. In tetros, there is ketotetros. In ketotetros, we will have one asymmetric carbon atom. Well, so there will be 2 to the power 1, there is 2 isomers, one will be D and one will be L. And what is that? That is called erythrulose. Its name is D-erythrulose. So when you know the structure of D-erythrulose, you know how to get the structure of L-erythrulose. Simply put a mirror, get the mirror image. So what is the structure of erythrulose? It's again very simple. You put the, it is CH2OH, C double bond O, then here you will have the this is your D-erythrulose. Now put a mirror image, then you can get the L-erythrulose. So this is constant, this is also constant. Now this is C, this side OH and H and CH2OH. So this is your L-erythrulose. Well, we will now then go for the our pentoses. While coming to pentose, I will first deal the aldopentose. Aldopentose, I will first deal. In the aldopentose, we will have, we have 5 carbon atoms. Out of these 5, 3 are asymmetric. So there will be 2 to the power 3, that is 8 isomers. Out of these 8, 4 will be D and 4 will be L. And what are these 4 Ds? Now they are ribose, D-ribose, D-arabinose. It is very important that we remember the names and structure of these pentoses and hexoses, tetroses and trioses. D-arabinose, then D-xylose and D-lyxose. These are the things, these are the 4 isomers of aldopentose. Now, their L configuration, L1 we can get it. There will be, similarly there will be L-ribose, L-arabinose, L-xylose and L-lyxose, L configuration. Now, we will have the structure of each of them. First, D-ribose. I will not show henceforth how we will get the L configuration of theirs. How I will draw the D and you can draw, if you like, the L, because just put a mirror and get the mirror image. So D-ribose, This is our D-ribose. This one. Always mark when I am saying D, it must be in this configuration. This is the last one. I mean to say the farthest asymmetric carbon atom. Then I go for the arabinose, D-arabinose. This is our D-arabinose. Then similarly xylose, this is your xylose. And when we go for the lyxose, it will be like this. This is the lyxose. Well, so this is what the pentases are. So these 4 pentases are there. They are the D isomers, and we can write their L isomers whenever we like them. Now coming to their what the ketone form, ketose form, we will have the ribulose and D-xylulose. D-ribulose and D-xylulose. Well, let me draw it. So you must not forget that. That they are the ketone form. So we can start with this CH2OH. Then next one C double bond O. Now 2 asymmetric carbon atom will come. So this last one will be CH2OH. So this one will be always in this form because it is D. So now only one change is there. Here it will be H and OH, and this is your ribulose, D-ribulose. Then D-xylulose, CH2OH, we started it like this, C double bond O, then CHOH, COH and H, CH2OH. This is your D-xylulose. So this is all about the pentases, and we will stop here for today. Next is your hexoses. In the coming class, I will begin with hexoses and its isomers. Now again with these pentases, we will have another interesting kind of isomerism. With also hexoses, we will find the same kind of isomerism, and both these isomerism I will be discussing in the coming class. For today, this much. Thank you.